Hello everyone, this is our last topic, series solutions near ordinary points, sometimes referred to as, in our homework we called it non-elementary solutions. So we consider a second order linear differential equation that's of this form, and we're going to rewrite it by just dividing by whatever the function is that's in front of y double prime, and then we define p of x and q of x accordingly. And just note that p of x and q of x are undefined when a of x is 0. Then we have a special definition. It's kind of a subtle thing, but I took this from Wikipedia. There wasn't a lot in the textbook talking about analytic functions. You can read this formally if you wanted to, but basically, if it's analytic, it's almost analogous to being continuous. So putting it, I guess, in what we might say is layman's terms. So as an example, here's a function that takes the form of this general second order differential equation that's homogeneous because it's set to 0. The coefficients are continuous everywhere because of x and 1 and x are the coefficients. But if we divide out the a of x, the x in this case, we get a situation where p of x is discontinuous, so we say it's not analytic. So analytic really, although it's a pretty formal definition here, some subtle points, and as you go on higher mathematics, you might study more about that. But for our purposes, it means continuous. Okay, so it's not analytic, so it's not continuous, or it's discontinuous. Obviously, when x is 0, because we get division by 0 here. So we define what we call an ordinary point, provided that p and q are both analytic or continuous at x equaling a. Otherwise, it's a singular point. So therefore, in this case, x equaling 0 would be a singular point. And then we have a theorem regarding that. And we say, suppose x equals a is an ordinary point, and that p of x and q of x are analytic at that point. Then there's two linearly independent solutions that take the form of our general power series, and talk about the radius of convergence, which is analogous to the domain. It's at least as large as the distance from x equals a to the nearest real or complex singular point, and the coefficients we determine by substitution, just like in the last section. So for this example, just want to illustrate that idea. And we're really not going to be majorly concerned about this. We're really only concerned about the mechanics of solving these problems, as we'll see in the last two examples of the course. That's all we got left. So if we divide everything by the x squared plus 9, we end up with y squared plus x over x squared plus 9, y prime plus x squared over x squared plus 9 times y is 0. So you can see that p and q are both not analytic when x squared plus 9 is 0. So that's basically what we're defining to be our singular points. So our singular points are when x squared plus 9 is 0. Or when x squared is negative 9, or x is plus or minus 3i. Almost did a little calc 3 thing there by putting a little hat on the I, but that's the imaginary unit I, of course. Okay, so what that means, so these are the singular points. That means that if you take an ordinary point, so that's something that where p and q are defined, okay, and you can pick anything you want, as we'll show here, And you consider the horizontal axis to be the reals and the vertical axis to be the imaginaries. There I go again with Calc 3. Then we're basically saying, let's say that we let x equals 0 be an ordinary point. Then if this is 3i and this is negative 3i, and 0 is the ordinary and these are the singulars, then we would say that the radius of convergence rho, okay, I guess I've been making my rho's a little fancier than that, right? I've been doing this for rho, would have to be 3. And this would be for the power series. The sum as n goes from 0 to infinity of c sub n x to the n, because the value of a, which is our ordinary point, would be 0. As opposed to, let's say, saying, so again, we could pick any ordinary point, such that p and q are defined. So let's say instead of letting x equal 0, let's say we let x equal 4 be the ordinary point. Well, if x equals 4 is the ordinary, and we've got 3i here and negative 3i here, and let's say that's 4, then the distance between the ordinary and the singular, this is going to be 5 units, because this is 3, this is 4, this is 3, that's 4, that's a 3, 4, 5 right triangle. So therefore, rho is equal to 5 for the series that's the sum as n goes from 0 to infinity of c sub n x minus 4 to the nth. Okay? Because the value of a is 4. That's the ordinary point. Okay, so we really don't have to worry so much about all that theory, and just be prepared to be able to handle examples like the next two examples. And the first one we want to find, okay, in both of these examples, we're just going to find power series solution in powers of x. We're not going to worry about turning them into elementary functions, although this first one has something special that happens at the end. And we don't have to worry about singular. I'm not going to worry about singular or ordinary points. But recall that we assume, so just like our previous problems, we assume that y equaling the sum as n goes from 0 to infinity of c sub n x to the n is a solution. And we have that y prime is the sum as n goes from 0 to infinity of, as n goes from 1 to infinity. So these were our theorems from the last lesson, of n c sub n x to the n minus 1th, and we also have that y double prime is the sum as n goes from 2 to infinity of n minus 1 c sub n x to the n minus 2 power. Okay, so that's c sub n. Okay, so then we make our substitution. So same as before. Okay, if we substitute, okay, we're going to leave this x squared minus 1 out in front. This becomes the sum as n goes from 2 to infinity of n minus 1 c sub n x to the n minus 2. And then we have plus 4x times y prime is the sum, n goes from 1 to infinity n c sub n x to the n minus 1. And then we have plus 2 times y is the sum as n goes from 0 to infinity of c sub n x to the n. And that has to equal 0. So that's all we did was substitute y double prime, y prime, and y in terms of the power series into our equation. Okay, now here we're going to distribute the x squared. Remember we said we're allowed to do this because the sum is really just an infinite polynomial. So we could dump the x squared in there. And this will be the sum as n goes from 2 to infinity. Okay, we'll have n minus 1 and c sub n. But then when we multiply x squared by x to the n minus 2 power, we just simply get x to the n because we're adding the exponents, and so therefore this would be x to the n minus 2 plus 2, which is just x to the n. Okay, and then we distribute the negative 1, so then it'll just be a negative, and then that series. Sum as n goes from 2 to infinity of n minus 1 c sub n x to the n minus 2. Okay, here we have the plus 4, and we're going to distribute the x. So we'll have the sum as n goes from 1 to infinity, the n c sub n stays, but then when I multiply this is x to the first times x to the n minus 1. Again, we're going to add the exponents, so we just get x to the n, because n minus 1 plus 1 is just n. And then this term, this series, we're just going to leave it as it is. And that has to equal 0. Okay, now there's something here that we do that's a little bit different, well, added concept as to what we've done in the past. Notice how all these powers, they're all n's except for the powers on x, that is. They're all, because we have to use the identity principle at some point. So all of these powers are n except this one, which is n minus 2. And if we compare the starting index, so therefore these powers differ, let's compare it to the n equaling 0, the actual series itself that's the solution. They differ, the powers differ by 2. And so do the indices. So therefore a shift on this term, shifting down by 2 units, will actually allow us to use the identity principle on the second and the fourth term. But the issue is the first and the third term. But the interesting thing here is that if you consider that this is starting at 2, what if you considered it starting at 0? So just imagine that this started at 0. If instead of 2, because if you plug a 2 in here, you get 2 times 1 c sub 2 x squared. So you get something that's meaningful. But if you plugged a 0 in, this n, if n were 0, would wipe out everything. And similarly, if you plugged a 1 in, this n minus 1 would become 0, and that would wipe out anything. So the argument here is this. We're going to start at n equaling 0, and that's because, or I'll just say cause, n equals 0 and 1 give 0 terms. Okay? So that's a little concept that you have to make sure you understand. And it's kind of simple. Don't make that harder than it is. Because, once again, I'm starting at 2. That's the meaningful term. N equals 0 and N equal 1 don't matter. Because if N is 0, this goes to 0. And if N is 1, this term goes to 0. So everything's 0. And then, as we talked about, we're going to do a shift on this guy. So let's say we'll shift this down by 2. And then this one here is similar to the first one. N equals 1 is a meaningful term because we'd have 1 c sub 1 x to the first. But N equals 0 would cause this to be 0. So here we're going to start this also at N equaling 0. And that's because N equaling 0 gives a 0 term. And then this one we'll just leave alone. Okay? So that's our plan. Let's go through and do it. So this one we could just change to 0 to infinity. And everything else stays the same. And then minus 1 c sub n x to the n. Minus here, we're going to shift down by 2 units. Okay, so started at 0 to infinity. But if we're doing a shift down, then if we decrease the index by 2, every value of n in the expression for the defining equation of the nth term gets increased by 2. And so therefore, this would be n plus 2. N plus 2 minus 1 is n plus 1. This would become c sub n plus 2. And x to the n plus 2 minus 2 is just x to the nth. Okay, and then for the third term, we said we're going to start it at 0. And everything stays the same. And the fourth term is just the original series that we'll recopy. And now notice that everything's set up so that we could use the identity principle. That is, all the starting indices are 0. All the powers on x are x to the n. And so therefore we can just peel out the coefficients. Don't forget about the negative in front of this one, and also the 4 in front of this one, and the 2 in front of this one. Okay, so therefore we have n minus 1 c sub n minus n plus 2 n plus 1 c sub n plus 2 plus 4 n c sub n, and then plus 2 c sub n, and then would have to be equal to 0. Alright, so now we're going to solve for c sub n plus 2. So we'll do it this way. If I move the c sub n plus 2 to the right, that would be positive. So let's do that. N minus 1 c sub n plus 4 n c sub n plus 2 c sub n would be equal to the n plus 2 times the n plus 1 c sub n plus 2. So again, what we want to do is solve. for c sub n plus 2. Okay, then I'm gonna flip-flop these equations. I just want this to be on the c sub n plus 2 to be on the left. So n plus 2, n plus 1, c sub n plus 2. But at the same time, from these terms on the right, I'm going to factor out a c sub n. And then I have n minus 1 plus 4n plus 2. Okay, and so let's clean this up. This would be n plus 2, n plus 1, c sub n plus 2 equaling c sub n times n squared minus n plus 4n plus 2. If I solve for c sub n plus 2, that would be, okay, this would give n, what's in brackets, oops, I'm sorry. Give you a second to catch up there. Okay, so I think you saw me factor out the c sub n and at the same time that I just kind of flip-flop these left and right. And it was left with the n minus 1 plus 4n plus 2. And I factored out the c sub n. Okay, then I just distributed the n there. Now I'm going to combine like terms here. So n squared plus 3n plus 2 over this n plus 2, n plus 1 times the c sub n. And that actually, the numerator actually factors as n plus 2, n plus 1. And everything cancels, and we just get c sub n. So we've shown, here's the recurrence relation. C sub n plus 2 is c sub n. So this is our recurrence relation. And similar to the examples we went over before, because n plus 2 and n differ by 2, we're going to need the even in terms of c sub 0, and the odd ends are going to be in terms of c sub 1. So, starting with the evens, n equals 0, 2, 4, etc. Okay, into the recurrence relation, when n is 0, c sub 2 would just be c sub 0. Because if n is 0, this is c sub 2 on the left, that's c sub 0 on the right. When n is 2, c sub 4, plugging a 2 in here for n, will be c sub 2. But c sub 2 is c sub 0. And when n is 6, or excuse me, when n is 4, c sub 6 would be c sub 4, but c sub 4 is c sub 0. Okay, so let's do the odd ones. So when n is 1, 3, 5, etc., c sub 3 is going to be when n is 1, but when n is 1, this c sub 3 is c sub 1. C sub 5 is when n is 3, but c sub 5 would be c sub 3, and c sub 3 is c sub 1. going in as 5, C sub 7, C sub 5. But C sub 5 is C sub 1, so that's C sub 1. So they're all C sub 1s. Okay, so now our solution, okay, so our solution y was the sum as n goes from 0 to infinity of c sub n x to the n, which is 1 plus c sub 1x plus c2x squared plus c3 x cubed, and so on. But we've got the odds and the evens. So let's break this up. We'll rate it as 1 plus c sub 2. It's not 1, I'm sorry. It's c sub 0. Okay, so now let's break up the odds and the evens. So c sub 0 plus c2x squared plus c4x to the 4th plus c sub 6, x to the 6th, and so on. Okay, and then I'll put a big plus here. That's the evens. The odds are c1x plus c3 x cubed plus c5 x to the 5th plus c sub 7 x to the 7th, and so on. Okay, but all the c sub 2s, 4s, and 6s, and 8s, and so on are c sub 0s. So we got c sub 0 plus c sub 0 x squared plus c sub 0 x to the 4th plus c sub 0 x to the 6th, and so on. And all the odd c's are c sub 1s. So c sub 1x plus c sub 1x cubed plus c sub 1x to the 5th plus c sub 1 x to the 7th, and so on. So let's factor out the c sub 0. We're left with 1 plus x squared plus x to the 4th plus x to the 6th, and so on. Then let's factor out the c sub 1. We're left with x plus x cubed plus x to the 5th plus x to the 7th, and so on. And now we just want to rate these as infinite sums. So as infinite sums, c sub 0, this would be the sum as n goes from, remember, as a power series, we always want to start at 0 to infinity. The only thing happening here are powers of x, and the patterns are x to the, there's really an x to the 0 here, so 0, 2, 4, 6, etc. So that would be x to the 2n, would give us the even numbers as the powers of x, and then plus c sub 1 times the sum, always starting at 0 to infinity, and these are the odd powers, 1, 3, 5, 7, and for the odds, the pattern of 1, 3, 5, 7 is represented by 2n plus 1. So you could actually stop right here for me. You could stop at that point. But the textbook, what they do is they take this a little bit further. Because I'm just going to want the, you've answered the question. I said power series in terms of x. You gave it, and that's it. But here's what the textbook did. They factored out an x to the 2n and made this c sub 0 plus c1x times x to the 2n, which further, because you can see that be c sub 0 x to the 2n, c sub 1 x to the 2n plus 1, because you're adding exponents there. So they factored out the x to the 2n, and then they further went and expressed this as c sub 0 plus c1x times x squared as a quantity to the nth power. And this basically geometric, fitting the form of AR to the nth. And so the sum the geometric sum is A over 1 minus R. And this is fitting the form of the sum of AR to the nth power of a geometric series. So A is the c sub 0 plus c1x, and the value of R is the x squared. And so that would be over 1 minus x squared. Okay? So remember, you can stop right here. You don't have to do anything fancy like they did at the very end of this problem. I've got one more example for you, kind of similar to this one, just kind of extra practice, and then that will be the end of the course. So we'll come back and we'll look at our final example when you're ready.